So now let's get into this idea. What is the idea of LIGO? Yeah.
So remember when we were talking about space-time curvature? Another way, like not another way, but maybe like a property of curvature is that it can stretch and compress things. That is because when you think of curvature, I know some people maybe think of like two-dimensional curvature where you're like literally like bending like something, like that. But in fact, compressing and stretching is a form of like three-dimensional curvature, 3D. Right?
Remember.
So, as Ray just said, we're talking about light waves. Now, the frequency of light, the wavelength of light is very, very small. We're talking, hundreds of nanometers, okay? And we're talking about a distance, right? We have light traveling, back and forth, reflecting off of mirrors, tens of kilometers, right? Actually reflecting a lot more than
we'll get into that.
Yeah. Anyways,
we'll get into that.
The point is that imagine we send 2 beams of light, and on one way, the light gets stretched, and the other light gets compressed. It's a combination of both and everything at the same time. But as we're recording the intensity of the light, we see that at one moment they are constructively interfering, so we get like a spike in our detection, and then a little time, like a very, very, very small amount of time passes, and then suddenly it's destructive, and then constructive, and then destructive and constructive. So what's actually happening is that the distance, while the light is traveling through these chambers, the wavelength, right, is being compressed, stretched, compressed, and stretched.
Because of the compression of space.
Exactly.
Because of the gravity wave.
As the gravitational waves are passing through the observatory, it's stretching and compressing space. And we actually are able to see this by the detection of this interference of the light going up and down, up and down, up and down. And yeah.
So, how does it work? That's the big question, right? How does this thing work? So the idea stems from something known as a Michelson-Morley, or from the Michelson-Morley experiment, and it's known as a Michelson interferometer, the idea that they use. So the Michelson-Morley experiment, just a quick history lesson here, pretty cool one, where Michelson and Morley, very clearly, wanted to prove that space was not empty. There was something called an ether that they had thought about that persists through all of space-time. And with this understanding of this ether, it needed to have traveled in a singular direction. So they devised this experiment, this interferometer, to basically test if this is true. So what they did was they set arms of equal length perpendicular to one another, where basically they would send light and force it to destructively interfere. Now, if it was destructive or constructive, I'm not entirely sure, but it's the same thing. It's just they wanted to measure a change in that intensity. So what they designed it to be, let's just say for now, was destructive interference. That means if, let's say, it moves in a certain way, theoretically what should happen is that we should see no light. That means they perfectly align. That means this width is exactly equal to this width. What I'm trying to show is the perpendicular widths are equal, and therefore no ether exists. Or, if there was an interference, they would prove that the ether does exist, because one of them is traveling faster than the other. That means there's something pushing it in one of the directions. Now, this experiment, obviously failed. The ether does not actually exist, but the idea of this experiment, the interferometer, and the way that they set it up was what was beautiful. So LIGO, very similar to this setup, just a little bit different, is basically very similar to this interferometer, where it has 2 perpendicular arms. However, 4 kilometers might seem a lot to us earthlings, but for gravity waves, where they're change in space is on the order of 10 to the negative 17 meters, right? 4 kilometers is nothing. So what they did to amplify that, they added these things, a little technical here, called Fabry-Perot cavities. Fancy way of saying they added a mirror. That's basically what they did. So traditionally, what the setup is, I don't even think I really went through this, but there's a light, there's a laser, sorry. There's a beam splitter that basically splits the light in 2 perpendicular directions, right? That one light ray splits in 2. One going parallel and one going perpendicular, right? That's what a beam splitter does. Then the mirrors on the other side of the arms will basically reflect that light back into the beam splitter, and then it will direct it towards the photodetector, which will then see if there was an interference of light. Now, again, as I said, the 4 kilometers, not enough. So what they did was they added extra mirrors such that once it hit the beam splitter, it would go to the edge of the mirrors on the arms. It would reflect back and forth over 300 times and then come back to the beam splitter and re-meet at the photodetector. So the idea behind LIGO and what they set it up, and this I know for a fact, so that it was destructive interference. So at all times, there was nothing seen on the photodetector. Because remember, to see something, just a little bit, out of absolutely nothing is easier than to see something less out of something. Because if it was constructively interfering, right, and they had detected a gravity wave, it would just destruct by just a little bit, just a little bit. So it would be really hard to detect. But if it was destructive interference to begin with, and the gravity wave had come in, just a little bit would have actually produced something. So you would be able to see that a lot easier. So that was their idea behind this whole thing. And in 2015, as I mentioned, a little bit after they had revamped the whole facility, they have 2 facilities, by the way, one in Livingston and one in Hanford. And both of them must agree with each other because, again, sometimes it can just be an earthquake or it can be something specific to that area that's not really general. That's why they have these 2 facilities. And they're thinking about expanding, I believe, to India. I think that's another country that's going to get it. So something like that. It's going to be crazy. But anyways, the idea is basically to verify that the information is right. And what they did was, when this gravity wave occurred in 2015, basically the movement of space-time, remember, it's not like it happens like, it does, well, technically, but the thing is, it's all about catching it. It's all about timing it. Because this gravity wave actually occurred for fractions of a millisecond. In that millisecond, they had seen a spike, as in something was detected at the photodetector, and then it basically went back to what the regular noise levels were. So if you actually search for LIGO results, it's a very, very famous picture. You might be able to see it from any Google search. You'll be able to see what I'm kind of talking about, how it's kind of the spike and then it dies down a little bit. And it's a little more complicated because there are actually two sightings, but the idea again behind it was that moving, that space-time, as Parker, as you were saying, that movement of space-time is what caused one of those arms to shrink a little more than the other. And that's basically what caused some of that interference. And that's how it works. That's the workings of LIGO.